lecture, but okay. We are going to talk about natural disasters during the course of this semester. And the thing I want to emphasize to you is that a natural disaster is only a natural disaster or catastrophe if it causes loss of life or causes economic damage, specifically a loss of property and other things. Without humans, there would be no hazard. It would just be a natural process. There are lots of benefits to these things that we call natural disasters. For example, when rivers flood, we have fertile soil, we have flat land to build on, we have waste flushing, we have water to drink and for municipal and commercial water supply. But when we build too close to the river, that's when we start to have problems with regards to economic damage and potentially loss of life. It's the same thing with landslides. Landslides are situations that are natural. They happen because of gravity, and they're only a problem when we build houses on slopes. So bear that in mind, that these are natural, see on the left side of the schematic that I drew, geoprocesses, natural things that happen on Earth because of gravity, because of the sun shining, because of rain falling, that only result in a hazard when humans are too close to whatever it is that's going on. We're actually going to end the semester looking at population increase, human population increase as a potential natural disaster. And what we are going to see with this is that there are more people on Earth. We have exponentially increasing populations of humans. They are moving increasingly to hazard-prone areas. And so we are going to have a situation where more and more people will be perishing, and there will be more economic damage through time as a result of just the fact that there are more people here. Here's an example of a natural disaster. The Fukushima reactor that we'll talk about later in the semester was at the wrong end of this. This was an earthquake outside of Tokyo that led to the Tohoku earthquake. These are pictures that are on the left-hand side before and the right-hand side right after the tsunami hit. So again, we're going to talk in detail about this. This is actually kind of a cool word, a chilling but cool word. The word is imanami, which is called a wave of purification. It's beyond a tsunami. It is a situation where the wave caused so much damage that you don't really have anything left. So they can cause a lot of damage, and we can't stop them. We cannot stop these natural processes. Right now, over the short term, we're also not going to be very successful with stemming population growth. So what we're going to try to do during the course of this semester, and you'll see humans increasingly doing, is to try to mitigate or lessen the damage. How can we cause less people to perish? How can we cause less buildings to be destroyed in the face of these disasters? You can see the syllabus for the types of disasters that we're going to talk about. And I include climate change in this for multiple reasons that we'll discuss later. And we divide the course into a couple different sections. Interior processes, which we'll look at first, that is stuff that goes on as a result of plate tectonics. So volcanoes and earthquakes and tsunami. And then we will go into the superficial processes, things like landslides and flooding. We'll go into atmospheric processes, so hurricanes, tornadoes, thunderstorms. We'll go out into space with meteorite impacts. And then we will also look at superficial processes such as drought, wildfires, and how that can increase famine, which is also sometimes a natural disaster. These things occur with varying degrees of warning. An earthquake, gosh, we've spent billions of dollars on earthquake prediction, and we're no closer to figuring out any sort of predictive technology for when an earthquake will happen. And at the other end of the spectrum, I would say, for the most part, volcanoes, we know when they're going off. It's very rare that people perish as a result of a volcanic eruption. So we'll look at these sorts of things as well. And the scope and the frequency and magnitude are really important when we talk about how to mitigate or lessen the damage. These are very simple things that we will talk about in a qualitative way for most of the semester. Frequency, how often it occurs, and magnitude, how powerful it is. And we're in a fortuitous situation where the power is inversely related to the frequency. That sounds like math to some of you, may be math phobic. All that means is that the more powerful something is, the less frequently it happens. We have earthquakes, for example, in Boston every other day, but they're so small we can't feel them. The scope is pretty intuitive. It's the area that's affected, and that can be from a very small region, so a localized landslide, to an enormous region, looking at some of the larger hurricanes that have come through, or in the case of large volcanic eruptions, they can have global scale, as can meteorite impacts. So frequency, how often, magnitude, how powerful, and scope, where is this localized? I will give you, and I hesitate with this because I don't want to go into too much detail, especially with earthquake and tsunami. Those are our first and third disasters that we'll talk about. But the things that we're going to be talking about are earthquakes and tsunami. Earthquakes occur because of tectonics, because there is a fracture in rock that's under stress in one or more directions. Here's a good example. Certainly you don't need to memorize these numbers or the effects, but here's a good example of the magnitude being inversely related to the frequency. You can see that small earthquakes, we'll talk about the moment magnitude scale, why we don't use Richter anymore. The small earthquakes happen about 1 million almost per year, less than 2.5, but we don't feel them. We can record them with seismometers. And at the other end of this increasing scale, over an 8, this is an enormous amount of damage, and they only happen once every 5 to 10 years. A little more often recently, the Earth's been rather noisy. We're going to talk about the San Francisco earthquake, and this is a science class, but I do dabble in policy and history, and the textbook that's optional is something that deals a lot with history. So the Great San Francisco earthquake, this was an interesting situation where there was a huge earthquake. It destroyed a lot of buildings, fires started, and fire extinguishing was hampered by the fact that there was so much debris in the roads. You couldn't get to the buildings that were burning. So what did we do? We bulldozed a lot of the city. We dumped it into the Marina District, so into the bay, and then we built more buildings on it. So not a great idea to have a bunch of unconsolidated materials in a coastal area that's on an active fault zone. But we'll spend a lot of time in California during the course of this semester talking about more details. So then what the city did was to draw people in, rebrand it as the Great Fire of San Francisco. The reason for that is because, yes, there was a lot of fire, but fire is a lot more preventable and controllable than earthquakes are. So they drew people to the area after the early 1900s by saying that the fires are over and we have put in all of these great new fireproof technologies. So they didn't say anything about the fact that it was an enormous earthquake and we built on very hazardous materials in terms of future earthquakes. Haiti, again, we'll talk about this. This was terrible, terrible tragedies on so many levels. We'll talk in detail about it. There's a case study in the book. And a lot of the problems here dealt with really substandard building materials. There's an adage among seismologists that earthquakes don't kill people, buildings do. And these buildings were just really poorly constructed with regard to being able to withstand an earthquake. Earthquakes are globally the highest number of people killed, and there is no warning. We're going to look at some ways that we can try to have a warning, some new technologies and some old ones, but we just don't have a way to predict earthquakes. And there's a lot of damage that occurs as a result of them. Secondary damage also includes other disasters. After an earthquake, oftentimes you have a landslide because you've destabilized the slope. And cities are crisscrossed with power lines, with gas lines, and so you can a lot of times have gas lines rupture, live sparking of electricity, and you can have explosions and fires for days after. What can we do? Well, we can't stop earthquakes. We also can't do much to prevent them from happening, or anything to prevent them from happening. So what we can do is to try to build buildings so that they can withstand the earthquakes, and we can educate people about what to do in the case that an earthquake happened, and also to have a disaster evacuation plan. So more on this during the course of the semester. Here's just a simple schematic diagram showing pre-earthquake on the seafloor, then under specialized conditions when you have an earthquake where one block of rock on the seafloor is thrown upward relative to the other, will displace water and cause a tsunami. So we're going to look at tsunami as well. We had two huge ones in the recent past, the 2004 Sumatra tsunami and then the Tohoku earthquake. And there's some statistics here. You don't have to memorize these statistics at all, but there's some interesting factors through the course of the semester with all these disasters in terms of magnitude and scope and some facts and figures about these things later. So this is also sort of an imanami in that there were land grabs after the tsunami came through because in many cases you couldn't tell property lines. There were no buildings left. The Japan tsunami we will talk about a lot. This is the biggest earthquake in a very long time. You can see the seawall being overtopped here. There was 5 minutes of continuous shaking, which the earthquakes rarely last that long. I will put in, nice time to say this, I'll put in some documentary footage of these disasters because I can sit here and show you PowerPoints all day, but it's really fascinating to see eyewitness accounts and documentary footage of these things. So there's a gruesome picture of what happened. Another picture of the aftermath of the Sumatra tsunami. They're expecting another one fairly soon off the coast of What can we do? Well, tsunami are a little more predictive. The earthquake itself is not, but we have travel times, especially if they are a decent distance offshore. There are travel times that we can say, okay, there was an earthquake. There may or may not be a tsunami. And if there is a tsunami, this is what you should be doing in the next several hours, potentially, if the earthquake was far enough offshore. So monitoring is important, but sometimes technology doesn't do what it sets out to do for reasons that we'll discuss in a couple of weeks. What can we do to lessen the damage? We cannot build in places, and we'll talk about the Hilo, Hawaii downtown after a tsunami there and how they rebuilt the town and they put the devastated area into really kind of parks, conservation land, so that if there's another tsunami in that region, it won't be devastated. The grass will be saturated and there won't be a lot of problems with death and destruction. We can also put in seawalls, although we'll talk about how the Sumatra tsunami was something that overtopped the seawalls there, which caused a lot of death and destruction. So we can't have an over-reliance and over-faith on engineered structures. So we'll talk about some of these structures as well. And we can also lessen the hazard by teaching people. If you feel the land shake, get to high ground. You are in a tsunami prone area, so you need to be especially concerned with signs of a tsunami. And a general understanding of the mechanics of tsunami is very important. So I will leave you here and go on to lecture 2 on the learning management system, and you can have a brief review of what I just said, and also an introduction to tropical cyclones. Thanks for listening.